Welcome to qnawire.
So for this problem, our initial data is that the radius of disk A is 0.3 meters and the radius of disk D is 0.115 meters. We can then calculate the mass moment of inertia for disk A, which is I bar A, as a half times the mass times the radius squared for disk A. And these values are known, so we can calculate this moment of inertia. That's a half times 30 kg times 0.3 squared. And so we get the mass moment of inertia for disk A to be 1.35 kg meter squared. We can do the same for the smaller disk D. So for disk D, the moment of inertia is a half times the mass of D times the square of its radius, Rd squared. And so this is a half times its mass of 5 kg, and we suppress the units, times the radius of 0.115 meters squared. And hence we get the moment of inertia, and we'll keep as many decimal points as we can to be 0.0330625 kg meters squared. So now we have the moments of inertia for disk A and disk D. The angular speed of D in the initial state, state 1, is given as 440 RPM. So this is before the spring is released. 448 revs per minute is equivalent to 46.077 radians per second. And similarly, the angular speed of D in the second state is given to be 176 RPM. Remember, there are 2 pi radians in every revolution and 60 seconds in every minute. So this is 18.4307 radians per second. So here we have a diagram of the situation, and we will let point P be the contact point on disk D and Q be the disk contact point on disk A. So P is the contact point on disk D and Q is the contact point on disk A, sorry. So this is contact point on disk A. So those 2 points will coincide where the two meet. So from here we can see that the linear velocity Vp is equal to the radius of D times the angular speed of disk D to the left plus the contribution of the linear speed of disk D, which is Vd, to the right. And this is equal to Rd omega D minus Vd. So minus Vd, we change the direction, all that to the left. That's Vp. The velocity, linear velocity of point Q is similarly Ra omega A to the left. So that's the point on disk A that's moving to the left. So the linear speed is then to the left. But we know that if we have rolling without slipping, these two velocities must be equal. So the velocities where these points coincide on each disk must be the same. So the speed Vq must be equal to the speed Vp. And so what that means is that Ra omega A is equal to Rd omega d minus Vd. So Ra omega A plus Vd must equal to Rd omega d. And we'll call this equation 1. So using the principle of the conservation of momentum and impulse, we initially have state 1 where disk B or disk D is rotating with angular momentum id omega d 1. Subscript 1 means state 1. We then have an impulse where the external impulse is due to the compressed spring being released. And the final state is one in which disk D rotates with angular momentum id omega d subscript 2 for the second angular velocity omega d2. It also has straight line momentum md vd. Disk A rotates with angular velocity or angular momentum ia omega a. So if we use this information and we take clockwise moments about B, we get the following. So the angular momentum of disk D in the state 1 is id omega d 1 plus 0 for disk A. Disk A is not in motion, it's not rotating. And this is equal to the angular momentum of disk D for state 2, id omega d subscript 2 plus Ra plus Rd, the radius of disk A plus the radius of disk D, times the linear momentum of disk D, md vd. Minus the angular momentum, since this is in the opposite direction, of ia omega a. So this equation becomes I bar a times omega a minus Ra plus Rd times md vd is equal to minus id into omega d in state 1 minus omega d in state 2. And we'll call this equation 2. So we can substitute numerical data into equations 1 and 2. And if we substitute our numerical data into equations 1 and 2, they transform as follows. So equation 1 becomes 0.3 omega a plus vd is equal to 0.11 times 18.4307. That's just equation 1. Equation 2 becomes 1.35 omega A minus 0.3 plus 0.115, the sum of the radii, times the mass of A, or the mass of D, times VD, 5 times VD. And this is equal to minus 0.0330625 times 46.077 minus 18.4307. And that's equation 2 with numerical values. So what we can do is we can solve 1 and 2 simultaneously. We have two equations with two unknowns. We solve 1 and 2 simultaneously, and we get omega A to be 1.7663 radians per second. And hence VD, we can substitute back omega A and get VD to be 1.58965 meters per second. And hence we can find WBC, which is simply VD over RA plus RD, so that 1.58965 over 0.3 plus 0.115. And so we get WBC to be 36.6, and this is revs per minute clockwise. And that's vector WBC. And similarly, our angular velocity for A is equal to 16.87, again in revs per minute, and this is in the opposite direction, that is anti-clockwise.